Well, hello and welcome YouTube. Mr. Robinson back here with yet another brand new exciting video, all math-based of course, and as always, it's an honor and a privilege to be serving you here today, as it is every day here in my virtual classroom. Hey, step on inside, and I got kind of a fast one for you. I got 8 problems of graphing basic exponential functions, y equals ab to the x form. No translations with h and k. I will show you what the appearance of that might mean, but we're just going to be graphing these. I think the last 2 of the 8 problems are where we come up with an equation based on it, and after we figure that out, it's all going to be good. Now, I'm going to be doing these without a table. I believe that I can show you on the first problem kind of how using a table would work, or like you can make a table, but when I say use of a table, I mean substituting values for x to get values out for y. And that's what I'm actually going to avoid doing. What I'm going to do is use the nature of exponential functions and what's happening with it. And again, this is without a translation property stuff. I think later, maybe a month or so from now, or a couple months from now, you might see me do another video that's the more advanced using an h and k and what happens when they actually translate. But until then, we're just going to leave it here. So I'm going to go ahead and get started, guys. And we are going to do the following. For each function, we're going to state whether it is a positive or negative exponential growth or decay function, and then state the y-intercept and state the domain and range, and we'll sketch the graph and its asymptote. Now, an asymptote is one of the main features of an exponential function, because what happens in these to the x power things is you can never get 0 as an output. You know, this is assuming no translation. I can't substitute anything for x to ever get 0. When this is positive here, I can't substitute anything for x to make this negative. There are certain barriers for which your graph does not cross in, you know, where your range is limited. And that's what's happening here. If I substitute 100 for x, this value is massive. If I substitute negative 100 for x, this number's tiny, but not tiny like negative tiny. 2 to the negative 100th power is 1 over 2 to the 100th power. So whatever that thing is, huge number on the bottom, it's basically 0, but it's not. 1 divided by some large positive number is still, it's a tiny number, but it's still positive. It's non-zero. And that's what this asymptote idea will be. Now, the asymptote is going to be the same each time because there is no translation on these. And I can straight up draw my first one right now. It's on the x-axis. The idea that there's a barrier here that we do not ever touch or cross. And I'm going to represent it as a dotted line each time there. So let's go ahead and graph these things. I'm going to start with y equals 3 times 2 to the x power. Now, this is in the form y equals a times b to the x power. Now, a is going to represent our y-intercept. Y-intercept is at 0, a. This is where it crosses the y-axis. There's only one of them, and this will always be the case assuming no translation. The b value represents the growth or decay factor. So I'm just going to write growth factor. I will state when it is decay. In this case, it is not. In order to be decay, you have to multiply by something that's going to shrink your value, something between 0 and 1. 2 is more than 1, so our values will grow. And when I say grow, I mean assuming we're looking at from left to right as we graph. So here's how this works. And you know, this is where a table could be of use. If I substituted 0 for x, and by the way, order of operations apply. That means you do the exponent first. 2 to the 0 power would be 1, and 3 times 1 would be 3. So if x equals 0, then y equals 3. And that's exactly why that ends up being the y-intercept. When x equals 0, this thing just turns into 1. And 3 times 1 is 3. That's how that goes away. Every time every time x increases by 1, you're going to be multiplying another 2 onto this thing from whatever you had previously. Right now I'm just at the number 3. When I substitute 1 for x, it would be 3 times 2 to the first. So I do 3 times 2, which is 6. So every time I increase x by 1, I'm going to be doubling my previous output, or at least the distance from the asymptote. This was 3 away, this is 6 away. If I increase x by 1 again, I'm going to be doubling my 6. Doubling 6 is 12. Obviously 6 out from 6 right there. Now I can't really fit the next one. I'll still intend to just kind of plot it. 12 times 2 would be 24. So if this is 20, it'd be 21, 2, 3, and 4, kind of up here. But you can see this takeoff formation. 2 to whatever power has another 2 multiplied to it, and that's what's happening. You can tell I didn't use a table, whether, you know, I'm not actually plugging in. You never heard me say 2 cubed is 8 and 3 times 8 is 24. I'm recursively taking the previous y value and doubling it to get the next one. And I think that's really kind of the fastest way of going about it. Now I still have things on the left to do. Does this go like this, and is it a parabola? No. It's not that. This is exponential. This approaches the asymptote because what happens is if I'm doubling my y values as I increase x by 1 going to the right, I'm going to then be halving my y values as I decrease x by 1 to the left, as I go to the left. If I did times 2 times 2 times 2, let's do divided by 2, divided by 2, divided by 2. And a better way of saying divided by 2 might be times 1/2, because I'm going to probably be thinking of these as fractions. I don't have a calculator in front of me, and I'd prefer to really kind of come up with it in that way. By the way, I never still stated all this information up here. I'll do it in a bit. I'll use this graph and kind of talk about it. 3 divided by 2 is 3 over 2, and 3 over 2 is 1.5. So you're going like that. You know, sometimes you need to know the number. Sometimes you just kind of need to have the visual idea of what's happening. I need half of this. So, okay, just draw half of it. I don't know. Maybe you can do that. Half of 1.5. Half of 3 over 2. Sorry. Half of 3 over 2 is multiplying 3 over 2 by 1/2. And that's 3 over 4. And that's, 3/4 is kind of like that. Halfway between 1/2 and 1. And that's kind of what's happening. And, I'm not really going to calculate. I mean, the next is 3/8, which is half of 3/4, and 3/16. And it gets really small, right? It gets really small. And when it comes to graphing these, I stated for my own students here, graph at least 2 points on either side of your y-intercept, of your y-axis, or plot as tall as you can go. And the 24 is probably out of reach for them. That's fine. But the idea is still in place on how that thing takes off there, and that's what this graph looks like. That's what this graph looks like right here. Now, what are some of the features on this graph that I wanted to mention? I need to state whether it is positive or negative in exponential growth or decay. I'll go ahead and tell you that this thing is positive. Let's use blue. Sorry about that. This is positive exponential growth. Now, how do I know whether it's positive or negative? Positive is when your a value is positive. A value is greater than 0. Because it is above the asymptote right there. It's not because it's going up. And that's something I'm going to make sure to state. And by the way, when you argue going up, it could be, if you could argue this is going up as well if it goes to the left. But I mean, it's not increasing as x increases. That's not why. Positive has to do with being above the asymptote here. And that's what's going to happen. You take a positive number and multiply by positive numbers, whether fractions or whole numbers or whatever, they'll stay positive or they'll stay above the asymptote the entire time. The growth has to do with b being greater than, not 0, but being greater than 1. And, b is going to be either greater than 1 or be between 0 and 1. See, b is the number that we multiply by over and over, that growth or decay factor. We're going to multiply by that number over and over to obtain new values. And in an exponential function, you can't have b be 1. Because if I multiply by 1 over and over, my value is remaining constant and is unchanging. That's not an exponential function. If I multiply by 0, then it will always be 0 over and over, which I guess is a constant as well and non-changing. If I multiply by a negative, it has an oscillation effect with regard to points, and it can only occur on integers, really, for a specific reason of rational exponents, not really working with negative bases. So b has to be a positive number. B is greater than 1. You are a positive exponential growth there. Now, the y-intercept, of course, was at 0, 3. And the last thing I wanted was domain and range. Now, your domain is going to be all real numbers every time for these. That's not going to change. That'll always be all real numbers. And your range for this one is y is greater than 0. It's asking you what y values exist in this thing. Obviously, it can't hit 0 as a result of the asymptote, which it'll never do for these. And we're positive, we're above. So if a is greater than 0, in this case, for non-shifting ones, y is greater than 0. All right, so that's what we have on that one. Now, I'm going to play around with a couple more things before I jump to number 2, and I think things will go a lot faster after this. Let me start by stating this, just a little teaser for transformations. If this said something like plus 4 right here, this would be an instance of a plus k. And what that would do is a vertical translation. It would take everything, I guess including my 4 that I just took. It'll pick it up, and it'll move all of these, including the 3/2. It'll move everything up right here. Your horizontal asymptote would now be at y equals 4. It would still be considered positive. This would be y is greater than 4. Everything would be shifted up 4 units just like that if you had something there, like a 4 there. And minus 4 would be shifted 4 down. Now, if there was something else in the exponent, like a minus 5 or something, you've seen some of these before with me with your minus h that we go to the right instead. This would have been translated 5 units over here. And that's like what this graph would have looked like here. So, but there's still a reference point to which I would be utilizing, which is not the y-intercept in this case anymore, right? It's not the y-intercept anymore, but it is a reference point. It's shifted 5 units away from there, and it's kind of a coolio bit to it. Anyway, we're not dealing with that. That's a little teaser for what can come a month or two from now when I make another video on it. Okay, now number 2. Now, one little problem, guys, is I have a little watermark right here behind me. If I move this thing, I'm not sure why it doesn't recognize that I'm connected to a smart. Before I was virtually connected to a smart notebook thing, so apologize for this watermark when I draw ones that are on the right side of the screen. There's nothing really I can do about it unless I shift it over the whole thing. Okay, do I have to get anything else? Sketch diagraph? Nope, that is all it. All right, number 2, y equals 4. Oh, I'm sorry. Before I do number 2, I'm very sorry. The last thing I wanted to do before I start these was give you the general behavior of all our graphs. We noticed this was positive exponential growth because of what A was and what B was. Let me hide some of the stuff up here and give you a very rough sketch drawing of the 4 different kinds of graphs that we're going to see. The first one that we saw in positive exponential growth, for y equals ab to the x, we can say, okay, if we have a greater than 0, positive exponential function, and b greater than 1, we've seen that graph, it's going to take on this form right there. If we have a is less than 0 and b is greater than 1, this is a negative exponential function, but it's still growth. And this is part of the thing I wanted to mention when it comes to, like, here's what it's going to look like that. It's going to go downward. So it's growth. It's growth, but it's negative growth, right? You say it's going down. That's not growth. Yeah, it's negative growth, and that's what those actually look like there. Now, if a is greater than 0 for positive again, but b is between 0 and 1, as I stated, multiplying by a fraction less, by a fraction less than 1, it won't be growth anymore. It's positive, but it's called decay. The graph is going to go down like this and approach the asymptote as we multiply by a fraction over and over and shrink it toward the asymptote as we increase. Basically, a flip version of this across the y-axis. And then when a is less than 0 and b is between 0 and 1 right here, we are going to have what's called negative exponential decay, which is, once again, it's going closer and closer to the asymptote there as we increase x from the underside. It goes up, but it's still considered decay because of its lessening effect from negativity. And that's what's happening there. So all 4 of these will occur, and like I said, positive exponential growth, negative exponential growth, positive exponential decay, and negative exponential decay. Those are the 4 different kinds of things we're going to have within that set. Okay, everything else should be a lot faster here on out, although we have new instances of fractions and things to take care of. Sorry for the watermark. Number 2. Oh, let me move myself before I do that. Sorry for the watermark. Number 2. Y equals 4 times 1/2 to the x power. Now your y-intercept is going to be at 0, 4. That's where we're going to begin this guy here. Let me draw the horizontal asymptote here at y equals 0, as they'll always be. And then the 1/2 is what we're going to be doing next. We're going to multiply 4 by 1/2 every time x increases by 1. Multiplying by 1/2 is also the same as dividing by 2, if that helps you for the integer math. 4 times 1/2 is 4 divided by 2, which is 2. And 2 divided by 2 is 1. And 1 divided by 2, or 1 times 1/2 is 1/2. And 1/2 divided by 2, or 1/2 times 1/2, I might have said that before, is 1/4. And you can see we become half of what we previously were as we keep moving to the right. Multiply by a half, closer and closer to 0. This is positive exponential decay. Now, let's go to the left as well. If we multiply by 1/2 going to the right, then we divide by 1/2 going to the left. I don't want to say divide by 1/2 though. 4 divided by 1/2 is also known as 4 times, flip this, 2 over 1, or 4 times 2, which is 8. We are doubling. If we are halving going to the right, then we are doubling going to the left, like that. So we are going to be doubling 8 to get 16, and I'm not going to bother to get 32 up there, but that would essentially be what would come next. So that graph is a curve that goes right here as it approaches the asymptote. And by the way, I want you to watch what I do with my arrows here once I get a much better curve. I want you to watch what I do with my arrows here. This is something that I honestly don't even know if I was taught it or if I decided to do it myself. Full arrow, because of course it would keep going. I mean, an arrow, because it would keep going. But notice how I draw, not tend to, I do. I draw a half arrow as we approach the asymptote to indicate, as we got to mention domain, to indicate that the domain is still an all real number set for x. It still goes forever left and right. And technically it still goes forever down. It's still diminishing its value as we take half of the previous number over and over. But because it doesn't go down toward negative infinity, I like to give that arrow basis as saying that it's going down and it's continuing, but it's approaching that. See, if I draw a full arrow here, suddenly it crosses the asymptote. There's no problem with it, especially when I feel like I'm the only person in the world who maybe even do this. I don't know if that's even proper, but if you ever see me graph rational functions, I do the same thing for those because they have vertical and horizontal asymptotes there. And you're actually bound to see a rational graph video coming up very soon on my channel. Okay, so anyway, we need the, this is positive, exponential, decay. And then it has a domain, of course, of all real numbers because, and what I wanted to state with that is there is no restriction on what I can substitute for x. I can substitute anything under the sun, and I will always get a y value, and that's what they're asking for a domain. Range is a little easier to see when you have the graph, but once you recognize what all these things all these graphs do with regard to the exponential behavior, these are either going to be y is greater than 0 or y is less than 0. And the graphing window range will help you as well. When it's not flipped over, you know that's going to be greater than 0 there. Just a little practice for now, just to make sure you still know how domain and range work. All right, I'm going to move on to number 3, as this probably keeps speeding up. Negative 4 times 2 to the x is well, it's kind of like any of these, but in a different way. So negative 4 times 2 to the x power. This one is now, with the negative 4 being your y-intercept. And of course, as I stated before, it'll stay negative because you keep doubling a negative number or halving a negative number, and it just stays negative. This is negative exponential growth because of the regard of multiplying by 2. It's going to be larger negative as we increase x by 1. Multiply by 2 again, and we get negative 16. And it really does seem to be the exact flipped version of what this was. This was positive exponential decay with regard to 1/2 for doubling, and this is negative exponential growth when it comes to doubling, or dividing by 2. Negative 4 divided by 2, negative 2 divided by 2, negative 1 divided by 2, half of negative 1/2, like that. And of course, the asymptote is here. Once again at y equals 0, unchanging as we approach that very closely, and we can draw a curve that flattens out on one side. It converges toward y equals 0, never hits. The word converges is what I said. It approaches it, and on this side it's taken off. Never vertical. Always, it gets super sharp, but never vertical on that. So what is this? This has a y-intercept of 0, negative 4. Something I probably could have written first. It is negative exponential growth. This is negative exponential growth because b is greater than 1. We're growing largely negative. It has a domain of all real numbers, and it has a range of y is less than 0. It's negative, all negative there. What color haven't I chosen here? Let's use this other blue. And lastly, on this page, y equals negative 2 times 1/2 to the x power. So we're seeing one of each. We saw positive exponential growth, positive exponential decay, negative exponential growth, and here comes negative exponential decay. So let's see if we can get the information first this time. A y-intercept will be at 0, negative 2. This will be negative exponential decay. And this should have a domain of all real numbers, and you can imagine that this range, because of no shifts in the way that the graph is done and it's negative, is y is less than 0. So we got the information without the graph as well. All right, so we start at 0, negative 2, and we're going to take half of these values. Half of negative 2 is negative 1, half negative 1 is negative 1/2, negative 1/4, and keeps going. The other side, we double it, so we get negative 4 double negative 4 is negative 8, double negative 8 is negative 16. These problems aren't as iffy as they can get. I think I kept these ones basic because I used the same one for different integrated math levels. I can do, without making them shift, I could do more advanced ones that are not going to be covered here, such as if I use 2/3, if I used 6/5 and things like that. I'm keeping the numbers pretty basic, so we kind of get that portion out of the way. If the numbers do get too confusing, if you have to do something like 5 times, let's do 2/5. I guess times 2/5 isn't that bad the first time because you multiply by 2/5 and you get 2. But then you got to do 2 times 2/5. And that's good to register in a table because when you have to use mixed numbers sometimes or any form of fractions and use a fraction on a fraction, I think it's a little better there that you have a table to work with. Now, when I say table, I don't mean substituting the x value into there. I just mean multiplying by another instance of your growth factor or your decay factor from your previous y value, from your previous distance from your asymptote. All right, that's number 4. I got 4 more to go, and hopefully it looks like it's going faster for us. Number 5. Now, this is different from number 4 in that it's not only not negative, but the a and the b are switched. On this one right here, we do have a y-intercept of 0, 1/2. It actually is on the fraction this time, so 0, 1/2. We're going to start right over here at the 1/2 mark. And we gotta double this, we gotta halve it and do things like that. So this is going to be positive exponential growth. It's a positive a value at 1/2. It's still greater than 0. And we are doubling, so it will be growing largely positive. So we gotta double 1/2 and we get 1, and then 2, and then 4, and then 8, and then 16. Again, not too clever with those numbers there. Take half of 1/2, it's a quarter. Take half of a quarter, it's 1/8. And we have a horizontal asymptote here at y equals 0. Unchanging from previous times. Woo-hoo. Okay. What else am I missing here? Domain and range. All real numbers. Range is y is greater than 0. Okay. This is the last one to graph. After that, we're going to be given 2 graphs, and we're going to write the equations from them. So you can see how it's kind of speeding up here at the end. This was a little different, though, because now we have an odd number with doubling and stuff, which isn't too bad on the doubling side. But on the halving side, we're going to need a little more help. And, this is one where I'm going to go ahead and draw a table for you. I'm going to draw an x, y, just so you have the idea of kind of what I was talking about before, if you ever want to use it. I'll put 0 in the middle for symmetry purposes. And let's just plug in a few values to this side, even if we can't fit them all. We'll see. And a few values on this side as well. Okay. So 0, -5 is, one of your points here. So 0, -5, that is the y-intercept. So that's me identifying it. Every time I increase x by 1, I should be doubling my previous output there. Now, this is not... I have to be careful when I put this because this is not the case for vertical translation. You should be doubling your distance from your asymptote, not just doubling the y value, unless you are doing the entire, plugging it in and evaluating the entire expression. So this is only doubling the distance from the asymptote, which of course our asymptote is at y equals 0. Anyway, so you double -5 and you get -10, and double -10. And you get -20, obviously negative exponential growth, and 3 you get -41, which we can't fit. Now, on the other side, though, we divide by 2. And dividing by 2 can come in one of 2 forms, either saying divide by 2, which is where we would get -5 over 2. Now, this is one of our only instances of a mixed, improper fraction that we might need to write as a mixed number that you should see here. So -5 over 2 is also known as -2 and 1/2. I'm not going to get too big into how you do mixed numbers. That's kind of assumed that you know. I guess you could use a calculator, but there's that. Now, how do you do -5 halves divided by 2? Well, you might want to say times 1/2 instead, because -5 over 2 times 1 over 2 means you multiply -5 with 1 and 2 with 2, and you get negative 5/4. Also a mixed number, so that would be negative 1 1/4 right there. Also another point applied. And for the sake of this exercise, let's do it one more time. Let's multiply by 1/2, one last time here, times 1/2. And you can see I'm making use of the table. I'm not plugging these values into here per se, which to some people arguably is faster. But this concept can still get you really fast if you... This is really just for me to store them so I know what I'm going to write. Otherwise, I'm not really doing much with it. But negative 5/8. So let's go ahead and plot those here. So we have 0, negative 5 right here. 1, negative 10 as we double, and 2, negative 20 as we double again. Now we're going to be taking half of that. So half, we get that negative 2.5. Negative 1 1/4. Now negative 5/8, that is really close to negative 1/2. It's negative 0.625. It's more than negative 1/2, which means it's a little further down from the 1/2 mark. Not much. Not quite in the 3/4 territory. I'd say that's pretty good there. Half of that, negative 0.3125, negative 5/16. I don't know there. You could obviously keep going. But we're good. So you're a tough graph. Make it really rough graph. I shouldn't keep singing because if I do, I wonder if I'll get a copyright block, even though I'm... Not that I make money off these. All right. It's really funny. You know, I play sports in the background of my things, and during the... I forget if it was the World Series or a divisional round of... championship round, a playoff round of baseball. I think it was, because it was Dodgers and Braves. And there was a copyright claim thing on it. Even though it's blurry there, it did recognize that it was like a Fox broadcast and it was doing that. All right, 2 more to do. These should be pretty fast. Oh, hold on, actually. Let me go back to this one. I didn't write out the things. It has a y-intercept of 0, negative 5. It is negative exponential growth. The domain is all real numbers, and the range is y is less than 0. Okay. Last 2. Now this is also negative exponential growth right here. Write an equation for each graph in y equals ab to the x form. Simple. We need the y-intercept, and that's going to represent a. And then we need the growth factor. As x increases by 1, what are we multiplying by each time from one y value to the next? And that's going to be b. So with regard to a here, now this is an asymptote on the y, on the x-axis there, y equals 0. So it's going to be on the y-intercept is a. So the a value in this case is going to be negative 3 because that is the y-intercept of 0, negative 3. Now the next values here are negative 6, negative 12. I went from negative 3 to negative 6. That's doubling it. I went from negative 6 to negative 12. That's doubling it. So your b value is 2. That's x as x increases by 1. There are other ways to do this using a system of equations, setting up a particular like x, y with another x, y, and then kind of solving for b and using that to solve for a. I'm not going to do that here, especially when there's no shift thing, but it also reinforces what we did when we graph, so I think this will help out. So this is going to be y equals negative 3 times 2 to the x power there. That's what that form is going to look like. And lastly, number 8, we have 0, 2. So our a value is 2 as we approach a x-axis asymptote. These can't be certain what they are. Don't assume that's 1/2. It doesn't even look it right there. So maybe we've got to look the other direction. It looks like that's crossing, that's crossing at negative 1, 6. And if you're not certain, we do see it cross again at what looks to be negative 2, 18. So as we're going to the left, we are multiplying by 3 from 2 to 6 and from 6 to 18. Does that mean that b is 3? Well, not quite, because we're multiplying by 2 going to the left, which also, or by 3 going to the left. That's part of a, as x is decreasing. We got to see what happens as x is increasing. So if we're multiplying by 3 going to the left, then we're dividing by 3 going to the right. But as far as b value, you still can't say 3. We're saying what we're multiplying by as we go to the right, which is 1/3. So this is a positive exponential decay graph right here. It is decay, and that's another way to kind of know. You put 3, but you see a decay graph, you say something's wrong with that. So this is going to be y equals a times b to the x power, like this. And that's the last problem. Now, before I do sign off, I do want to make mention of the importance of the following. Notice how they do not use parentheses when they're using a whole number b value, such as this one. There are no parentheses here. There are no parentheses here. But when you look at a problem with a fraction, they do have parentheses. I'll let you know here and now, you are required to use parentheses if you're writing an equation with a fraction, because both portions need to be raised to that exponent. This is not required, but you'll see me write it anyway. So when you see this first problem over here, negative 3 times 2 to the x power, I prefer that look personally over negative 3 times 2 to the x power like that. So you always see me use parentheses, but it's not a requirement for an integer. It is for a fraction. Okay. All right, so guys, that'll do it for this one. This is Mr. Robinson. Thank you so much for watching, and later down the line, you're going to see one where I'm doing shifting of asymptotes and stuff. It's going to assume you know a little bit about what I just spoke about here, so it makes that part easier, and then the h and k stuff will come into play, and we can talk about how the range is affected from that, and kind of what we do there. All right, so that'll do it for this one. This is Mr. Robinson. Thank you so much for watching, and I will see you in the next one.